Okay, let's go over the syllabus. Here's all you really need to know. Raise your hand if you're actually registered for this class, meaning you didn't email me, you didn't fill out the Google form, you signed up with a CRN number. Cool. Those of you that are raising your hands, you have to come. That's the only way you pass this class is by coming to class. You get one workload unit for passing the class. That means it counts towards not towards graduation, but towards being a full-time student and financial aid purposes. If attending is an issue and you don't need the unit, you're welcome to drop the class and get added to Canvas. It really doesn't make any difference at all, other than you won't be getting a pass and a pass grade. That's really all you need to know about the class. Is if you wanted one unit because you need a unit, then you have to be enrolled, and to pass, you have to come. And not just come, you have to be actively engaged, right? You can't come and do whatever in the background. You should come and participate. That's why you're here, right? To get more help with math, I would assume. So that said, I probably should actually look at the syllabus because I probably wrote some things that I thought were important at some time. So let's go ahead and scroll through this real quickly here, if I can. All right. So, oh, by the way, I'm James. Nice to meet you all. Please call me James, but if you can't handle that, which I totally understand, you can call me Mr. Parmenter or teacher. I'm not a professor, but people like saying that word. So you can call me professor, just know I'm not one. Those are all fine. Grading, I just talked about it. The reason there's so many reminders is because every quarter a bunch of people are like, I see I'm getting a 15% in the class, I'm worried I'm going to fail. And I don't enjoy getting those emails so often. So please know if you're not enrolled, your grade doesn't matter. If you are enrolled, please come. If you aren't enrolled, also please come. What else? Classes. Oh, passing grade is 70%. We are meeting 29 days. We'll talk about that more in a minute. Which means a passing grade is coming 21 times. The reason we're not meeting 30 days, even though there's 30 days of instructions, is we are not having class on this Friday. I will be gone. I have a funeral to attend. So yeah, my grandma died, but she was very old, lived a great life. So it's a good funeral. I mean, right, there's good funerals. Anyway, as far as attending, if you don't come in person, but you still want to attend via Zoom, which someone could right now, or you want to watch the class video later, I would ask you to please, 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 please fill out this attendance form. That's not the attendance form. Failure. Sorry, one moment. Why is this so challenging? Okay, sorry, this is awkward. Sorry, that's where your attendance grade is located. Apologies. The attendance form is somewhere else, which we will get to in a minute. But I'll just say the reason I'm asking you to fill it out is because part of my job is to click buttons or not. Okay, it's broken. Part of my job is to count the number of students I serve every quarter. It has to do with how our department gets funded. So the more students we serve, better it is for everyone if we approach those numbers. So please, when you attend, whether it's in class filling out the form going around or virtually, or you watch the video later, please fill out the form that's right here. If I can maybe click on it, there we go. It's pretty easy. Your email goes in there, as well as your student ID number, your first and last name as it appears in Canvas, although that's not as big a deal anymore. It used to be a bigger deal when I was trying to sort people and make things happen. And then what class you're attending and how you attended. And then the date, when you put in the date, please put in the year correctly, because otherwise things get all out of order in my Google Sheet. So yeah, that's it. It's not hard to fill out, but please do it when you attend, not here, right? So if you're attending on Zoom or watching the video recording later, please do that. What else is important here? Let's see, not a lot. If something outside of the class is impacting your success in the math, please don't hesitate to talk to me about it. This class is open to everybody. I try to be pretty welcoming and engaging, and I like people. So you're always welcome to ask me questions or give me feedback or say, I feel like one year someone said they had a really hard time reading what I was writing, asked me if I can use a thicker pen. So I did, and it's made a big difference for everybody. So if you have other useful feedback, I'm happy to hear it and try to accommodate things. Something I also get often is sometimes I talk kind of fast. It's not my usual vibe, but certainly when I'm teaching, I tend to like speed things up. I don't really know why, other than I just do. So I will try to slow it down, but I find it challenging. But I'll try. What else? Let's see. Our class meets Monday, Wednesday, Fridays right here. You're all here, so you know this. Most of this class involves me showing examples. This class is not really good for like both with the number of people and the board space, not great for working in groups or doing things like that. So I will try to have you do problems on your own or like with a partner on occasion, but a lot of it's going to be me showing. You should definitely ask questions though, right? That's how you're going to get your questions answered, right? If I do something, you're like, I'm not sure about that. What did you like? Don't hesitate to ask. You're probably not the only one thinking it. And I might have made a mistake, right? I definitely, not on purpose usually, make mistakes. So if you think I've made an error, please let me know, and I will certainly correct it or say or kind of address why you might have thought that was an error if it wasn't an error. Accommodations, if you have formal accommodations. Someone's knocking on the door. If you have accommodations, I will certainly accommodate you. This class doesn't really have a lot that needs accommodations. Things are recorded. There aren't any tests or quizzes or exams or homework. But if you need something, happy to do it. If you do want to record something on your own, that's also totally fine. But the class is recorded and will get posted on YouTube and well in the Canvas and then linked to YouTube. Zoom, we all know how to use Zoom at this point. Yeah. Sure, we could all read that silently real quickly. Yeah. Okay. And then there's other resources to get more help. Oh yeah, there's office hours, which I totally skipped by, which we'll talk about. There's math drop-in, which is in the library, which is staffed by student tutors and occasionally people like myself who are what am I? I'm a math specialist. People like myself and Grant and Ryan and Casey, but Casey's more other math. We also sometimes work down and drop in, but my office hours are listed somewhere. Somewhere. This is not the best place to find them. Really, I should just go over to the modules, which is where anything important actually is. So this is where I'll actually put important stuff. Let's go to the student view just for a moment. Just so you don't see all the things that aren't there yet. So, oh yeah, I forgot. There's some derivative review because you definitely need to know how to do derivatives, to do antiderivatives. So if you feel rusty on your derivatives, take a look at the video I posted from last spring. There's also a handout which you could do and answers to that handout. Or I should say the answers to the handout are on the recording. So this handout goes with this recording, and then there's the notes for it, and you can kind of see me do it and also do it yourself. There's also another derivative worksheet and answers. So again, I think it's worth your time to review derivatives if you feel rusty because you have to know derivatives to be able to competently deal with antiderivatives. It's kind of the whole name of the game. And then below that, we have some useful links, like the class attendance form, like the Zoom, like my office hours, which are on, let's see, when are they? So they're Monday, Wednesday from 11 to noon in drop-in. Tuesday, Thursday from 1:40 to 4, also in drop-in. And Monday, Wednesday, Friday, right after class over in CADS, which is the Center for African Diaspora Student Success. It's located on the second floor of the South Silo. Anyone is welcome to all of those office hours. Yeah, that's where I'll be. And then you can also, just so you know, you can also find the other specialist office hours at the AATC website. So if you go to the AATC website, there's also lots of other things you can get help with, like chemistry or physics or other things. But if you look at the math tab and scroll down, actually, I don't think our office hours are listed on here explicitly right now. Let me double check though. Oh, yep, they're right there. So you can find where Grant, myself, Ryan are. Duff can help with math, but he's usually occupied with physics students because they need all the help they can get. And Casey also can help with math, but usually is occupied with physics students. So really, you should see Duff and Casey if you need help with physics. If you need help with math, you should come find me or Grant or Ryan. Or you can also, somewhere, oh, I forgot about Mary Claire. Mary Claire also has office hours. She's a grad student, but she's great. She's excellent for help with math. And I thought Claire was on here. Claire has virtual office hours, but I don't see where they're listed. They might not be for everybody, so maybe I'm a liar. So lots and lots and lots of places to get help. Also, I think as I mentioned before, but I'll say it again, in math drop-in, which meets Sunday from 3 to 7 and Monday through Thursday from 10 to 5, starting not this coming Sunday, but the next Sunday. So drop-in starts on Sunday, October 5th, which it probably says on there somewhere. Yep, right there. And those are, again, student tutors, but occasionally you'll see myself and Grant and Ryan there. Then back to modules, see what else is important on here. Grant's website I refer to all the time. Lots of great resources on there. My website, total trash, not helpful at all. I mean, there's like my office hours on there and the classes I teach, but everything's in Canvas. Here's the 17B syllabus from the math department in case you're curious what's coming your way. And then this is actually very useful, I think, to kind of help you see how integrals and area and the Riemann sum work. We'll probably take a look at that next week sometime. Dell's exam dates, when I thought everyone was taking Dell's class, so I forgot that Burke was also teaching it. I'll add her exam dates on there as well. And then there's some handouts, some antiderivative practice rules, some summation formula proofs, which I think is on the discussion sheet for Dell's class, some of them. How to integrate. And then all the chapters of your textbook in case you need them. Cool. Water. All right. I know it's kind of fast, but are there any questions? Who's had class today already? So I should better question. What time does Burke's class meet? And what time does Dell's class meet? Okay, so everyone's had class today. There's another one. Oh my God, how am I so not into it? Who else is teaching 17B? Oh, he teaches two different sections of it. Ah, I see. Okay, good. I don't feel quite so crazy. And that makes me wonder if which Canvas he put me in. Well, I'll check that out later. Other questions or comments? Time is it? Half past. All right, so we meet till the hour, whatever hour is coming up next, because it's 1 something. So we meet until 2. I guess we can do some math. I would imagine in whoever's had a class today, you probably talked about antiderivatives. I see some no's. Okay, so who was in someone in Burke's class? What did you guys talk about today? Okay, cool. And how about the Dell's class? Cool. Well, then we'll start talking about antiderivatives also because since we're not having class on Friday, I feel like we're missing a day, which is unfortunate, but so we'll start talking about antiderivatives and maybe we'll start talking a little bit about sigma notation. Sure. I should probably make it so you can see this. Let's put this over here. Let me fix the view first before I start doing anything too crazy here. Yeah. Okay, come on. All right. Also, just in general, if you see me writing things that you can't see, like if I get too low or too high, usually too low is a problem. Let me know. Also, before we get going here, so day is September something, 24th. Let's see how that looks. Okay, this is how not great. Like you can see that back here, but like it's not excellent. But I think the only other option is turning off all lights, which I don't love because it's so much easier to see that though. I think this is worse. That's much worse. You don't do that. I don't like. Okay, who would prefer all the lights off? Who would prefer some of the lights on? I think the lights off have it, even though I would go for lights on. But I lose. Okay, so we'll try this out. That's probably partially also why I opened the windows because I had a feeling this was coming. Let's see. I need something else here. 1 second. Oh, I need to grab that back. Hold on a moment. Where'd you go? Come back over here to my screen. I really need to get this fixed. Cool. Cool. Or somewhere. One moment. So let's talk antiderivatives. Yeah, all right. So yeah. I can spell derivatives. Maybe I can spell. I feel like there's too many V's in there. Derivative. No, okay. So when you think about antiderivatives, you're undoing the derivative. Or as I would probably prefer to say, you're trying to find the function you would take the derivative of to get the thing you started with. So for example, if my function was, say, f of x equal to x to the fourth plus the square root of x plus 1 over x to the sixth, before I do anything, I actually want to rewrite this because it's much, much more straightforward to anti-differentiate powers of x when they're written as just x to a power. So I would rather write this as f of x equal to x to the fourth plus x to the 1/2 plus x to the negative sixth. Well, I've got some interesting shadows on my face here. That's kind of fun. All right. So I'll remind everybody that the derivative of x to any power is that power times x to the 1 less power. So to undo that, we're actually going to do the opposite things in the opposite order. So instead of multiplying by the power and then reducing the power by 1, we're going to increase the power by 1 and then divide by instead of multiply by the power. So to anti-differentiate x to the fourth, and typically the notation here is if you're just given a function and you want to write a function name for the antiderivative, use the capital letter until we start using the integral notation. So I would say the antiderivative is capital F of x, and it's going to be x to the fifth divided by 5 plus x to the 1/2 plus 1 divided by 1/2 plus 1 plus x to the negative 6 plus 1 divided by negative 6 plus 1. Plus, and we'll talk about this more, a constant, which we'll get to in a minute. But first, before we get to that, I kind of want to get out of the way of this thing in my eyes. And this is can't really do that though, because this is very much here. I don't have to write there though. Well, next time. So I would prefer to write this in the following way. The x to the fifth over 5 is fine, but you could write it as 1/5 times x to the fifth if you prefer. Either one of those is okay. Here, 1/2 plus 1 is 3/2. I don't really want to write x to the 3/2 divided by 3/2 though. I really want to write it as multiplied by 2/3. And over here, negative 6 plus 1 is negative 5. I'm going to write this as minus 1/5 times x to the negative fifth. We could check if we wanted to. You can always check an antiderivative by taking the derivative. If I took the derivative of this, the 1/5 hangs out. The derivative of x to the fifth is 5x to the fourth. The 2/3 hangs out. The derivative of x to any power is that power times x to the 1 less power. And over here, minus 1/5 times the negative 5 comes down. And negative 5 minus 1 is negative 6. And the derivative of any constant is what? I'm in the way. I'm totally in the way, right? No, I'm not. I feel like, okay. But I'm a little in the way for some people, I feel like. Is that, yeah, okay. I'll try to do something about that next time. Not that you should ever need to do this, but I will point out, right, 1/5 times 5 is 1. You get x to the fourth. 2/3 times 3/2 is 1. You get x to the 1/2. And negative 1/5 times negative 5 is 1. You get x to the negative 6. Exactly what we started with. When you find an antiderivative for a function, or as I say, the general antiderivative, we always tack on this plus c, because technically we could have added any constant, plus 7, or plus 2, or plus pi, or plus the square root of 5. Any of those has a derivative equal to 0. So when you're finding an antiderivative, you're actually finding technically a family of antiderivatives that all are the same function, except they might differ by a constant. Let's see, what else do I want to say here? I think that's it. All right. So, in the vein of trying to have you guys do some stuff as well, why don't you all try this one? My function is little g of x is equal to, sure, 4x to the seventh plus 3 e to the x plus 2 cosine of x. And I want you to find the antiderivative. So it's always hard to decide how much time to let you work on a problem for. But we'll move along here and say, so I would say don't simplify right away. This is going to be 4 times x to the eighth over 8. In general, just like when you differentiate something or take the derivative, when you anti-differentiate something, any constant multiple hangs out, is what I say, or sticks around, or you just keep it there and then you anti-differentiate the function it's multiplying. So we have 4, the constant multiple, times x to the seventh. Our antiderivative is the 4 hangs out. We multiply that by x to the eighth over 8. In a similar way, the 3 hangs out here, and the antiderivative of e to the x is e to the x. Kind of unexciting, right? E to the x is special. It's its own derivative. It's its own antiderivative. And then for 2 cosine x, the 2 hangs out, and the antiderivative of cosine isn't negative sign, it's positive sign. Right? The derivative of cosine is negative sign. The antiderivative of cosine is, wait, let me say, the derivative of cosine is negative sign. The antiderivative of cosine is positive sign. And then we slap on a constant. The only simplification I would make here would be rewriting 4 times x to the eighth over 8 as either 1/2 times x to the eighth or x to the eighth divided by 2. Something you probably want to be aware of is that for the trigonometric function sine and cosine, there's a cycle of derivatives and antiderivatives. So if you start with, say, f of x equal to sine of x, if you go down differentiating, the derivative of sine is cosine. The derivative of cosine is negative sine of x. The derivative of negative sine of x is negative cosine of x. And if you go one more step, the derivative of negative cosine of x is positive sine of x. And then if you go the opposite direction, you get the antiderivatives. So the antiderivative of sine is negative cosine. The antiderivative of negative cosine is negative sine. The antiderivative of negative sine is positive cosine. And the antiderivative of cosine is positive sine. It's an easy way to remember what's happening. I usually just think about it as that for antiderivatives of sine and cosine, it's always the opposite SIGN sign, right? If the derivative is positive, the antiderivative is negative, and vice versa. That only works for sine and cosine, though. Okay, let's see what else to say here. So here's what's challenging about anti-differentiation. Unlike derivatives, where there's very kind of just set rules for anything you do, for antiderivatives, there are not so much. There are some specific rules for certain cases, but when you get to functions that are more complicated, we have to kind of look at it and say to ourselves, well, this kind of looks like that kind of thing, and we're going to try this method, and it might work. And it might not, and they might have to try something else. So don't get kind of stuck in the mindset of, well, we see this, we definitely do this. We kind of have to think about what you might try. And I would say the first thing to know really is that before we try anything, we should simplify our expression. So if I'm trying to say, find the antiderivative of f of x equal to x to the 6 plus the square root of x divided by x squared, I don't just have x to a power here, or at least not yet. What I really am trying to say is we can't anti-differentiate each of those x to the 6th and x to the 1/2 and x squared individually because they're not individual. They're connected through division. So before we can anti-differentiate this function, we're going to rewrite it. We're going to rewrite it as f of x equal to x to the 6th divided by x squared plus x to the 1/2 divided by x squared. And then simplify that as x to the 4th plus x to the 1/2 minus 2 is negative 3/2. And now anti-differentiating it is straightforward because you just have x to a power plus x to another power. We can use what I usually refer to as the anti-power rule. And we say the antiderivative of x to the 4th is x to the 4 plus 1 divided by 4 plus 1. And the antiderivative of x to the negative 3/2 is x to the, negative 3/2 plus 1 is negative 1/2 divided by negative 1/2. I feel so in the way. And of course, we should simplify this, specifically this part here. I'm going to rewrite this as capital F of x equal to x to the 5th over 5 minus 2 times x to the negative 1/2 plus c. Dividing by negative 1/2 is equivalent to multiplying by negative 2. So just trying to think here for a second. At this juncture, any function you knew how to take the derivative of previously in 17A or whatever calculus class you took last time you took a calculus class, you should know how to find the antiderivative of that derivative. So we've already covered a few functions, like we know that let's just make a list. We know that the derivative of x to a power is that power times x to the power minus 1. I already said this. So we also know that I'm just going to start using the notation that we all want to use anyway. So this notation, which bears some conversation later on, but for now, when you see this integral symbol, we're just going to say that that means we're finding an antiderivative. There's more to say about that, but we have to learn some other stuff first. But for now, we'll say if you want to take the antiderivative of x to a power, you're going to add 1 to the power and then divide by the new power. And of course, we're going to add a constant. And that works almost all the time, except for one very important case. What number is really, really, really not okay to try to divide by? Right. So what power here would be problematic? Right, negative 1. So it doesn't work. You can't anti-differentiate x to the negative 1 and get x to the 0 divided by 0 plus c. Instead, we know that the derivative of the natural log of x is equal to 1 over x, which is x to the negative 1. So we know that the antiderivative of 1 over x, or x to the negative 1, is, I'm going to amend this in a second, the natural log of x plus c. But it's actually a little bit better than that. Better is probably not the word you would choose, but I'm going to choose better. It's the natural log of the absolute value of x. And the reason that's true is because, so many reasons actually, but the main reason is, here's what I would say. When you anti-differentiate something, you want the domain of the function or the resulting function to be at least as much as the original function. And that sounds kind of weird, but here's what I'm saying. The natural log of x, let me scooch this up a little bit. This is a good picture to keep in your mind. Here's what the natural log of x looks like. In fact, I've actually technically written this derivative incorrectly, although I'm sure you would all agree it's correct, but I didn't really specify the domain here. Here, the derivative of the natural log of x is 1 over x, provided that x is positive. Right? You don't get to take the derivative of the natural log of x and get the left side of the you don't get to take the derivative of the natural log of x function and get the left side of the 1 over x function because it's not defined there, right? Natural log of x is only defined when x is positive. So its derivative is only defined when x is positive. You can't differentiate a function where it's not defined. So with that, but over here, 1 over x is defined everywhere x is not equal to 0, right? 1 over x looks like this. Kind of like this, if I was a better drawer. Here's your y equals 1 over x function. And we would love for the derivative to have as much domain, sorry, not the derivative, the antiderivative to have as much domain or more. So our antiderivative here looks like the natural log of x function, but it's been reflected across the y-axis. So it's actually y equal to the natural log of the absolute value of x. I know that's probably more than I need to say here, but that's why we actually need the antiderivative of 1 over x to be the natural log of the absolute value of x, because we need all of that domain. Okay, a few other things. I'm not done with my list. There's more to add to this list. Paper is going all over the place. Some other derivatives we know. We certainly know that the derivative of e to the x is e to the x. So the antiderivative of e to the x is also e to the x plus a constant. And I'm trying to think of every function I can before I start talking about the trig functions, but I think we're there. Are there any other functions left? I don't think so. Okay, there's a few, but wait those a minute. So the derivative of sine of x is cosine of x. So the antiderivative of cosine of x is equal to sine of x. By the way, I know I didn't say it. When you write this antiderivative, it's the antiderivative of cosine of x, and this dx over here means with respect to x. So it just means x is the variable that we're anti-differentiating with respect to. And again, there's more to say about that when we start talking about intervals. We got a few more trig functions to go here. The derivative of cosine of x is negative sine of x. And we usually don't write it as the antiderivative of negative sine. We say the antiderivative of positive sine of x is equal to negative cosine of x plus c. Don't forget the plus c. Some other trig derivatives. The derivative of tangent of x is equal to secant squared of x. So the antiderivative of secant squared of x is equal to tangent of x plus c. The derivative of cotangent of x is... Any volunteer? Here's what I always remember it. The derivative of tangent is secant squared, so the derivative of cotangent is cosecant squared with a negative sign. And then the antiderivative of cosecant squared of x is negative cotangent of x plus a constant. Two more to go. They also kind of have a similar pattern as the tangent and cotangent. The derivative of secant of x is secant of x times tangent of x. And the antiderivative of secant x times tangent x is secant of x plus a constant. And I won't say lastly, but close to lastly. So if the derivative of secant is secant times tangent, the derivative of cosecant is cosecant of x times cotangent of x, but it's negative. The way I remember where the negatives are for derivatives is every cofunction, cosine, cotangent, cosecant, has a negative derivative. And similarly, the antiderivative of cosecant of x times cotangent of x is equal to negative cosecant of x. And I think, nope, there's one more. There's one more thing you need to know. I believe, although it's been a while, right, since whenever we took the last quarter of calculus, you probably learned that the derivative of the arc tangent of x, or if you prefer, the derivative of the inverse tangent of x, so they're the same thing, just written different ways, is 1 over 1 plus x squared. And so it's also the case that the antiderivative of 1 over 1 plus x squared is equal to the arc tangent, or the inverse tangent of x. We'll see. To my knowledge, I think those are all the functions we have to be able to know the derivatives and antiderivatives of going into this class. Unless you can think of something I'm missing. Right, because we don't talk about arc sine. Or at least I don't think we talked. We shouldn't have talked about arc sine in 17A. Everyone's like, maybe. Probably not. If they did, I can see Del doing it though. So what time is it? How much time do I have? Okay. All right. So here's what I would say about these derivatives and antiderivatives. They're totally fine. You do need to know them because the expectation already is that you already know all this, right? You know all these derivatives, so you know all these antiderivatives. You're just going the opposite direction. But then we're going to make it harder, because of course we're going to make it harder. Why would we not make it harder? So what if I said I want to find the antiderivative of f of x equal to sine of 4x plus e to the 2x. And this is where I think things get a little bit interesting. So I have a good idea. I kind of know what the parent function is. I know that's more of a graphing term, but I feel like it still applies. I know that the antiderivative of e to the x is e to the x. I know the antiderivative of sine of x is negative cosine of x. So I'm pretty sure the antiderivative of sine of 4x is going to be something with a negative cosine, and the antiderivative of e to the 2x is going to be something with an e to the 2x, but not quite. But that's where my guess is going to start. So my guess, which is going to be wrong, negative let's use my appropriate, my capital F. I know I went back to the other notation. We often go back and forth at this stage. My guess for the antiderivative is negative cosine of 2x, sorry, 4x, not 2x, plus e to the 2x, plus c. This is wrong. We're going to fix it, but I want you to see that it's wrong. How do I know it's wrong? Let's take the derivative and find out. So if I take the derivative here, this is where we have to remind ourselves of the importance of the chain rule. I have the derivative of negative cosine of something more complicated than x. I have an outer function, negative cosine of some stuff, and an inner function, the stuff, 4x. So when I differentiate this, the derivative of negative cosine of something is positive sine of that something. But then what do we have to multiply by? You can show me on your fingers. Right, the derivative of 4x, which is 4. In a similar way, if we differentiate e to the 2x, well, the derivative of e to the something is e to the something multiplied by the derivative of that something. And the derivative constant is 0. But look, our derivative is not what we needed it to be, right? Or we wanted our derivative to be sine of 4x plus e to the 2x, and we got sine of 4x times 4 plus e to the 2x times 2. Luckily, it's easy to fix that because we can multiply functions by constants, and that doesn't affect the derivative or antiderivative process. So I can take my answer here and multiply the negative cosine of 4x by, let's see, I want to get a 1/4. So that the 1/4 times 4 cancels, so I'm going to multiply this by a 1/4. Similarly, I want to multiply this by 1/2. So the 1/2 times 2 cancels, and I'm going to do that here as well. So my actual correct antiderivative is going to be capital F of x equal to -1/4 times cosine of 4x plus 1/2 times e to the 2x plus c. So here's what I usually try to say. If taking the derivative of a function would have made you multiply by a constant because of the chain rule, meaning your argument was like 4 times x or 2 times x or a multiple of just x, what almost always happens is our antiderivative makes us divide by that same constant. So for example, we could say that or we could ask, what's the antiderivative of secant squared of 6x, and be pretty confident, very confident, that the answer is going to be tangent of 6x divided by 6 or multiplied by 1/6 plus c. Because we know that when we take the derivative of tangent of 6x, we're going to get secant squared of 6x multiplied by the derivative of 6x, which is 6, which will cancel the 1/6. This is a very kind of basic version of what we will eventually call U substitution. But these are kind of the easiest examples. I do want to caution you, though. This only works if the argument of your function is just a straight up multiple of x. And that's kind of not true. If it's a linear function of x, so it could be a multiple of x plus a number. So just to kind of expand on that, example, James, sure. The antiderivative of e to the 5x plus 1 dx is going to be, well, the antiderivative of e to the stuff is e to the stuff, but then we have to divide by the multiple of x here. So divide by 5, or I would rather write it as multiply by 1/5. Because when you take the derivative of e to the 5x plus 1, you're going to get e to the 5x plus 1 times 5, and the 5 will cancel the 1/5. What time is it? Yeah, cool. So I want to point out, this does not work if you have anything other than just a linear function of x in your argument of your function. If you try to anti-differentiate something like cosine of x squared and say I'm going to say it's not equal to, because it's not, but if you tried to say it was equal to, say, the antiderivative of cosine, which is sine, and then you tried to divide by the derivative of x squared, which is 2x, no dice. Definitely. If you try to take the derivative of this, you have to use the quotient rule. And it's going to be much, much, much uglier than cosine of x squared. In fact, cosine of x squared is kind of famously not anti-differentiable. There is not a function that is the antiderivative of cosine of x squared. So you can't do this. So this thing we're seeing here only works if it's a function of a multiple or linear function of x. That's probably a good place to end today. So, no class on Friday. I'll see you all on Monday. Have a lovely weekend.